Okay, let's get started. Last time we were talking about injective, surjective, and bijective functions. Okay, that's a function from a set to another set, and we had some properties that we talked about. Now things get a little bit more interesting now, because now we take two functions and we combine them in some nice way, okay? And so the way we combine functions, today we're talking about composition, how to combine a function from A to B, and then add in another function from B to C. And in total, you'll get a function that has a domain A and codomain C. Okay, and so we want to talk about, if you know if F and G are injective or surjective or something like that, can you tell if the composition is injective or surjective? And vice versa. If you know that the composition is injective or surjective, what can you say about F and G? So here's an example question. If F composed G is surjective, must F be surjective? True or false? That's the type of question that could be totally on a test. It's a good type of question. And you should change everything here. You should change surjective to injective and surjective to injective and see if every permutation of this type of problem, see if you can solve it, okay? Okay, so let me just remind you function composition and really fast. Maybe I'll just say, if F is a function from A to B, and G is a function from B to C, then what I can do is I can compose F and G. I can make G O F. Okay, this means start with F and end with G. Function composition is read from right to left. Why mathematicians do that? I guess I have a vague idea of why this notation is preferable over the other notation where FOG, but let me just put it like this. GOF is a function from A to C. And it's defined like this. GOF, it's a function. That means it takes an input, let's say X, and the output it produces is like this. I plug X into F, and then this Fx is an element of B. And then I plug that Fx into G, right? Because Fx is an element of B. And G's domain is B. So I can plug that into G and then I get an output. You've probably seen this before in your calculus class, composing functions, chain rule and stuff like that. And if I had to draw a small picture of this, I would draw it like this. You have A, then you have B, and you have C. So X would go to Fx. That's what F does. And G sends Y to GY, right? That's G. So what FOG does is it sends X, it passes through B, and it gives you G of F of X. Okay, that's GOF. It goes straight from A to C. Okie dokie. That's what composition looks like. Okay, so here's an example of that. Here's a function f from z cross n to z. I love those Cartesian products. Let's get that poll set up. One sec. Okay. Don't vote quite yet. Let me read the question. So f goes from z cross n to z, and g goes from z to z cross z, and there's two formulas for it. Calculate this composition. Plug this pair 3, 2 into the function and see what you get. Okay, try it out. Right, so you definitely can't have A or D because D was 6 and 6 isn't a pair of integers, right? The output of GOF has to be a pair of integers. This is what I call a type mismatch. The object isn't even the correct type of object. So you can immediately rule out this answer, okay? Always do type checks. That's in computer science too. Okay, so let's calculate now. F of 2, 3, let's plug into G. And well, F of 2, 3, I just do 2 minus 3. So it's, oh no, I do 3 minus 2. So I have G of 1. And G of 1, I output like this. The absolute value of 1, comma, 2 times the absolute value of 1 plus 1. So that's just going to be 1, 3. And that's option C. That's all there is to it. Oh, I plugged in the wrong number? Wonderful. Wonderful. Okay, so let's do the other way around. Whoops. But you guys know how to do it. It's coincidentally giving me the same answer. I think that's a complete coincidence. Let's try the other way. So f of 3, 2 is going to be 2 minus 3, right? So f of 3, 2 is 2 minus 3, which is -1. So I have g of -1, but you see g can only output, it takes the absolute value anyway. So it doesn't, so that's why it ended up, g is kind of like an even function, right? Remember even functions from calculus? So because of that, I know that this is the absolute value of -1, comma, 2 times the absolute value of -1 plus 1, which is coincidentally 1, 3. Coincidence. Well, maybe not a coincidence because this g is an even function. Okay. Nice. So maybe ignore this first part because I screwed it up. Okay, let's move on to the next question, unless there's questions about this one. I have a question about this one, actually. Is this function g surjective? A side question. It's not surjective. Why? Ooh, nice. You'll never get negatives. Exactly. Very good. Very good. See, absolute value here in the definition of G, right? So it looks like you can only get negatives. Oh, sorry, you can never get negatives. It never outputs negatives, negative pairs. So for example, you would never be able to get something like -1, 2, right? But that doesn't mean it hits every positive pair, right? Can you give me an example of a positive pair that G never hits, where both components of the pair are positive? Burgess says 0, 0. Give me positive ones. Ayad says 2, 2. And okay, great. Can you justify that? I think some of those answers are correct. Can you justify it though? Y is here, for example. Also, 2, 2 is not in the image of Z, so GZ. It's because, give me a one-word answer as to why this is not in the image of G. Exactly, Nick got it. Odd numbers, right? Because second component, because 2 times x plus 1 is always odd. Or maybe I'll just say second coordinate should be odd. Nice. And very good. And one more thing. Is G injective? No. Okay, and why is not? Why not? Nice. Excellent. Great. I just proved it. Okay, really, you guys are getting really fast with this stuff. Very good. I just proved it. I just gave 2 examples of numbers, different numbers that output the same output, right? That give the same output. So it was 2, 3, and 3. Oh, no, sorry. That was for GOF. I'm looking at G1 and G -1, right? So the answer is no. G -1 is equal to G1. Nice. Good. Okay, great. So it's good. When I give you a question like this, don't just answer the question only. Try to come up with a new question and see how you can answer those. That's going to be a good way to study. Okay, let's do another poll question now about compositions, of course. So now I have 2 bijections, f and g. So this notation, I wrote f comma g. I'm just saying that f and g are 2 different functions with the same domain and codomain, okay? So f and g are 2 bijections, in fact, from R to R. And let's assume that g of 1 is 2 and f of 2 is 3. Can you calculate this? F of g inverse of 3, okay? Can you calculate that? And I don't even tell you what the functions are. I just give you a couple information about that function, okay? Give it a shot. Ooh, this one's a big oof. Looks like the answers are very split, although there was a majority on D. Let's figure that out. Let's figure that out. Can someone remind me what an inverse function is, by the way? If f, let's say if h is a function from a to b, then h inverse is a function from where to where? From b to a, right? Exactly. It goes back. It switches the domain and codomain. And let's say h of x equals y. What does that tell you about h inverse? H inverse of y equals x, exactly. It just switches the, yes, if h sends x to y, h inverse undoes that. It sends y back to x. So think of inverse as undoing. H inverse undoes h. Just like how square roots undo squares. You know, think of it like that. Oh yeah, Control Z, exactly. And speaking of Control Z, because I'm not taking the inverse of one function here, I'm taking the inverse of a composition of two functions, right? So let's say I type let's say you open Microsoft Word or whatever you use and you type in A and then B. And then you press Control Z twice. What's going to happen? It's going to delete A and then delete B, right? If you type in A, B, and then press Control Z twice, it's not going to delete A and B. It's going to delete B and then A. It does them in the opposite order, right? Think of it like this. Like if I put on my socks and then put on my shoes, how do I undo that? I don't take off my socks first and then my shoes, right? I take off my shoes first. I do the last thing. I undo that one first. So what I'm trying to say is that if I take the inverse of FOG, I have to undo G. I have to undo F first. Here I do G and then F, because remember function compositions from right to left. So here is, this thing represents G first, then F. And when I take the inverse, what am I going to get? Am I going to get G inverse F inverse, or am I going to get F inverse G inverse? Which one do I get? The first one or the second one? Everyone's saying second. And now you're saying first because I because I hinted you. It's definitely the first one. Remember Control Z. If I type in baseball and then I hit undo, it's gonna undo ball first, then base, right? It does them in the opposite order. So this is something I call so this is saying undo F, then undo G. So I undo them in the opposite order that I performed them in, okay? So how do I apply that to this problem? Let's solve this problem now. If I want to calculate f of g inverse of 3, how can I simplify this? How can I simplify this expression before evaluating it? Exactly, do f inverse of 3 first. This is g inverse O f inverse of 3, which I can write as g inverse of f of inverse of 3. And now it's just a matter of calculating, because I know f of 2 is 3. So here I'm going to use two things. I know f of 2 is 3, and I know g of 1 is 2, the information that was given. And since f of 2 is 3, what's f inverse of 3? It undoes, it goes back, right? If f puts 2 into 3, if f turns 2 into 3, then f inverse will turn 3 back into 2, exactly. And the same for g. G inverse will turn 2 back into 1. So if I want to calculate f inverse of 3, I just did it, I get 2. Right, because f inverse of 3 is 2. And then g inverse of 2 is 1. So it looks like there was enough information to solve the problem. The answer is D. Okay. Okay, if I put my socks on, then my shoes, to undo that, I have to take my shoes off first, then take off my socks. I can't take my socks off first, unless I'm a magician or something. So this reversal operation, this fact that inverses reverses operation, that I call the shoes and socks theorem. That's what I like to call. Sachs-Schuster. Okay. And this is something, if you take more algebra, you're going to see Sachs and Schuster theorem a lot. Ordering for composition matters. Remember how in fields, multiplication is commutative? X times y is the same as y times x. For functions, composition is not commutative. So you can't just do FOG is the same as GOF. Okay, you have to be very careful with stuff like that. Okay. Any questions about this one? Ooh, it's only true for bijections. Ah, you have to be very careful. So here, let me move this away and let's talk about that, what Tamsil just said. You have to be very careful. Let's make a little remark here that composition is not commutative. You can have an example of function two functions f and g from R to R. And the reason I make them from R to R, they have to have the same domain and codomain if I'm going to compose them each way. So maybe I'll say it like this. You can find f and g from R to R such that FOG is not the same as GOF. Does anyone know any quick examples? Even if you give me bijections. Even bijections. You can give me two F and G's that are bijections, and still it's not going to work. Can someone give me an example? I can use this example above. Well, this example didn't give any specific functions. Ooh, nice, James. X cubed and x plus 3 cubed. Nice. That's a really good example. I can simplify that a little bit more. Let's take f of x to be 2x and g of x to be x plus 1. Because then I don't have to cube anything. If I want FOG, I would do this, f of g of x, which is f of x plus 1, which is 2 times x plus 1, which is 2x plus 2, okay? And if I want GOF, I'm going to do g of fx, which is g of 2x, which is 2x plus 1. And you can see these are different. See? So I can, even if I have bijections, composition doesn't necessarily commutative. Okay. This is very different from fields. Just as a fun fact, bijections form something called a group, which is a different structure from field. It's a little bit more general, and it allows non-commutative operations like this. So we don't talk about groups in this class, but anyways, it comes up in other math. Maybe you'll see later. Okie dokie. Let's go to this last poll question here. So I have two more functions, f, g, from R to R, and assume that f is injective and g is surjective. Which of these four functions here can you conclude are injective or surjective? And this might take a little time. So let's get question 3 going. Which of these functions must be injective? Okay, so can someone give me a reasoning for, because the answer, the majority answer was C. So can someone give me the reasoning for that? Nice, 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 nice. The composite of two injective functions is always injective. Exactly. And that's a little theorem that you can prove. Nice. So theorem, composition of two injective functions is injective. Very good. All right, straight from the notes. Okay. So the composition of two injective functions is injective. Here I'm composing f and f. So that's f is injective. So it's f twice. That's still injective. Good. So the answer is C. And then since there's only one answer, you can kind of metagame this and say, oh, so it can't have been any of the others. But let's say that it wasn't a multiple choice question. Let's say that it was a multiple select question. You could more than one of answer could have been correct. Let's say that. I'm telling you how would you know which of these is going to be injective, which of them wouldn't be injective? Ayad is saying this one, A, F composed G, could sometimes be injective. That's true. It could sometimes be injective. But the question says when which of the following must be injective no matter what. So can we find an example where FOG is not injective? Where F is injective, G is surjective, but FOG is not injective. Can anyone give me an example? I need to think about this a little bit when I do a problem like this. So let's think like this. FOG means G first, then F, right? So I have G going from R to R, and I have F going from R to R, and I do G first. So let's say G is surjective. Maybe I can make it so that G sends, let's say G is not injective. Definitely G would have to be non-injective, right? If G was injective, then FOG would be a composition of two injective functions. So it would be injective. So I've got to pick a surjective function that's not injective. What's a good one like that? So let's say G sends these 2 points to the same point. So G is not injective in this little picture, although I've yet to come up with a legit example. And then F I want to be bijective, right? So let's say F switches these two, or F has to be injective. So let's just say it switches these two numbers. Okay. Then if I try to do check FOG, FOG is going to do what? FOG is going to send this point here to this point here, right? FOG is going to send this point to this point. And it's also going to send the second point to the same place, right? So here's an example where GOF is not injective. And I know this diagram is crazy, so maybe I'll try to make it less crazy. These 2 points go to the same place under GOF, but can we give a specific example? This is actually a little bit tricky. I have an example in mind, but I think it's going to be tricky. So let's try to give G from R to R and F from R to R. And instead of giving a formula for G, can you draw a graph? How about that? Can you draw a graph of a G that is, let me say like this. What did we say? Surjective and not injective. And for F, let's say injective, and it could be surjective if you want. Okay, some people are saying 2x. So wait, let me make sure I understand. Which one do you want to be 2x? And hold on, guys, I have to actually refresh my screen here. F. Okay, which you want F to be 2x? Okay, I'll do you one better. Why don't we just let F to be just x? This is called the identity function because it doesn't do anything. The output is identical to the input. It doesn't do anything to the input. So this is called the identity. You're going to see identity function a lot. And G, can you give me an example? You can't do x squared. X squared isn't surjective. It only hits non-negative numbers. So x squared wouldn't work. It's actually kind of tricky to come up with a function that's not injective, but can you draw the graph of it? Here, I'll draw the graph of F. Well, we all know what that looks like. It's just a straight line, right? X cubed. Ah, but you see x cubed. Nice. Woo. Nice. X cubed. Okay. You guys are getting good ones. You guys are getting good ones. Ln x. Nice. Nice. You guys are getting good ones. I can see a couple problems. If I chose, let's say I chose ln x. I'm not going to write down all the details. If I chose ln x, the problem is ln x is only defined for positive numbers, so it doesn't have the right domain here. Okay, if I pick sine x isn't surjective. It only hits numbers between -1 and 1. So sine x won't work. X cubed is surjective. That's true. Sorry that I'm going so fast at this, so just watch without taking notes. But x cubed is surjective. That's true, but it's also injective. So this won't function as a counterexample. Absolute value of x only hits non-negative numbers. So that's not surjective. X cubed minus x. I don't know what that looks like, but I'm trusting you. X cubed minus x is surjective. I think you might be right. X cubed minus x is surjective. Yes, if you do something like this, here's a surjective function because it hits every number on the y-axis. Any number on the y-axis has a corresponding point on the graph. But I want to say that this point here is hit 1, 2, 3 times, right? So this function is not injective. Good, very good. So this will work. This example will work. You can, I'll leave you to check that if I take g of x to be x cubed minus x, then what we were trying to see, FOG is not injective. Actually, I don't think we need to. I think this is actually pretty quick. Can anyone concretely tell me 2 inputs of FOG that go to the same output? One and 0. Very good. If I plug x equals 0, then FOG of 0 is going to be f of g of 0. And if you plug g of 0, you're going to get 0. And then you plug that 0 into f of x, you're going to get 0. Right? You're going to get f of 0, which is 0, because g of 0 equals 0. Okay? And how about x equals 1? Very good. F of g of 1 equals f of g of 1. G of 1 is 0 because that's the way we can, I'm assuming whoever made this function had that in mind, that there's a bunch of, this function has multiple roots. So I'm going to get f of 0 again, which is 0. So you can see these two inputs, different inputs give the same output of 0. Excellent. Very good. Okay, so what was the strategy for this? Try to come up with a function that's not injective, that hits 0 more than once. And this function crosses, I think another, yeah, I gave this example on this line, but I guess I could have just given the origin as an example. Let me see, erase here. Another example is, since there's 3 roots, there's 3 places where g is 0. At -1, 1, and 0, this function is 0. So this function is not injective because it hits 0 multiple times. Okay? So that's the strategy for a counterexample like this. Very good. Speaking of counterexamples, we've got about 15 minutes left. I'll give you some time to think about one problem here, or 2 problems. Okay? So, and this is more general than R and R, so you can't graph it necessarily. Okay, so here's the setup. I have 2 functions, f and g, so that g o f is defined. And let's assume that g o f is surjective. Does f have to be surjective, or does g have to be surjective? Can you prove or give counterexample? Okay, so prove for counterexample. Very typical type of problem. True or false? Okay, let me give you 10 minutes to work on this, and then I will take up one of them, or maybe I can take up both of them, okay? Okay, let's take this up. So you have a composition of 2 functions that's surjective. Does it have to follow that f itself is surjective? Ooh. Some people think that both f and g should be surjective. Somebody says no. So let's give it a shot. Ooh, nice. You draw a diagram. Nice. Nice. If you give an example, okay, let's see. So f, okay. So I have a couple of ideas for examples. So one idea is take f of x, okay. So maybe f, let's take all my sets to be the real numbers here. A, B, and C, let's take them all to be the real numbers. And then you'll take f to be the function from the reals to the reals. That's what? Just x, the identity map. And then take g of x to be x squared. Okay. But then this g isn't, but then if you calculate GOF, you're going to get x squared. And that's not surjective, right? That's not going to work, I don't think. Let's try drawing a diagram. Instead of taking real numbers, why don't we use finite sets? Because we didn't say here that A, B, and C had to be real numbers or any subsets of the real numbers. I could have just taken some finite sets. Let's say A is a set of 3 points, maybe. How many points should I put here in B? 3 again, okay. How many points here should I put in C? 3 again, okay. So how should I map this points out? How should I map things out? Should I send this? So the first function to act is going to be f, right? And then g. So what should I do? We're trying to find a counterexample to A right now. How should I define this here? Maybe I'll start us off. Maybe I'll send, I want to find an example where f is not surjective, right? So why don't I do this? Let's send the first point to the first point, the second point to the second point, but the third point, I'll send it back up to the second point again. So this way f is not surjective. This f is not surjective. Can I define g to make this injective? Ooh, nice. Somebody says make this only have 2 points. Let's try again then with third example. So here's what I'm looking for, by the way, just to be concrete. I'm looking for an example where f is not surjective. Well, let's say GOF is surjective, but f is not surjective. I actually don't think it's possible if you put all 3 points in every set A, B, and C. If you make them all have 3 points, I don't think it's possible, because no matter what I do to G, if I make G to be really surjective, maybe like this, I don't know, there's no way that GOF is going to hit this point, right? There's no point here in this first set that ever travels to this third point in the third set, right? There's no point that hits this last target. The example we did in the previous question won't work, because in this example, f was a bijection. And we're trying to find an example where f isn't even surjective. So f certainly can't be a bijection, right? This function is surjective. So this example is not going to work. Let's try a similar example, except let's take out a point from B. I have a feeling this isn't possible. I have a feeling this isn't possible. Let's see. Oh no, I think it should be possible, but we have to pick the right points here. Take 1 out of C. Okay. Nice. Exactly. That's going to work. That's going to work, Ishav. Exactly. So why don't I take this function here? This is the same as the one I did before. This f is not surjective because f doesn't hit this third point here. So f is not surjective. And now I can pick b to say be this function. Very similar looking function. So in this example, f is not surjective. Okay. But what about GOF? Is GOF surjective? In this example, is GOF surjective? Yes. Okay, why is that? Why is it surjective? Because I'll just say this point is hit, right? This point is hit by this point over here, right? This first point in A hits this first point in C. How about the second point in C? That's hit by the first point in A. So basically what I'm saying is that each point in C, you can follow it back and there's a path to a point in A or from a path in A. There's a path from a point in A that leads to C. Same with this, that leads to this first point in C. The second point in C, same logic. There's a path. That's what failed in the second example, right? This example didn't work. This third example does work. Okay. Each point can be hit by some point in A. Each point in C can be hit by some point in A. Okay, so A is false. So the answer to A is no. And there was a counterexample here. These two first examples didn't work. Sometimes you have to try a couple things. The answer to B, let me just say, is yes. The answer to B is yes, and you can prove it. Okay. Okay, so I'm 3 minutes over time, so I can't really spend any time proving B. And if you got to go to class at 10:10, you got to go. So, so that's it for today's class, I think. So I'll see you guys next. If you want to stick around, I will prove B now, and I'll record it so that everyone can see. Okay. So let's go over how to prove B. And I'm going to record this so that if you have to go, you can go. See you guys later. Those of you guys who got to go. But let's prove this. If GOF is surjective, then G is surjective. Okay. Let's prove this. So remember what it means to prove. Remember what it means to prove that a function is surjective. It means that every point in the codomain has to be hit. So why don't we get this straight here? So here's A, here's B, and here's C. F goes from A to, oh, sorry, no, G, which one goes from which to which? F goes from A to B, right? And G goes from B to C, and GOF goes from A to C. So what I want to show, if I want to show that G is surjective, I have to show that every element of C is hit by some element of B, okay? And there's no assumptions here aside from G O F is surjective. I'm not going to assume anything about F, and I'll still be able to conclude that G is surjective, okay? Watch this. Watch this. So I need to say, take an arbitrary target in C. So let's call it Z. Let Z be an element of C. We want to show that that C is hit by some element in the domain of B. The domain of G, and the domain of G is B, so I need to find some element of B that hits C. So I want to show there is some element Y in B such that G of Y equals Z. And you might be asking, why am I using Z and Y? What about X? Well, I'll use X for elements of A, Y for elements of B, and Z for elements of C, just alphabetical order, just to keep things straight, notationally. Okay, so I want to show there's some Y that hits Z. Well, what do I know? What do I know about Z being in C? I know that GOF is surjective, so what can I say? Since Z is an element of C, what can I say? Yep, I know Z belongs to C. Exactly. There's an X that in A that hits Z. Exactly, because I know GOF is surjective. So there's going to be some X that hits this Z, right? So since GOF is surjective, very good. There exists some X in A such that X hits C under GOF. So GOF, G compose F of X should be Z. And what that means, if I just use the definition of GOF, that's G of F of X equals Z. Okay. But I wasn't trying to find X. I was trying to find Y. So what can my Y be? I know that there's some X. Exactly. Why don't I let Y to be this fx, right? So if we let Y to be f of x, then Y is an element of B, and G of Y is G of f of x, which is Z, as required. And that's QED. So that's the proof. Okay. So Burgess is asking, how do I know that f of x hits y? The thing is, I'm not saying, I don't know what y is yet. At this point in the proof, there is no y. I haven't found y yet. What I do is I let y to be this. I've defined y to be f of x. Literally have defined it. So think of it like this. Let me try to draw a diagram. So I know what I do is I have my three sets A, B, and C. And I want to say hit this element here. Let's call that Z. I want to hit this target Z here. What I do is I say, okay, well, I want to hit this target Z using some element of A. One of these, from this A position, I want to hit Z. What I do is I say, okay, I know that, oh, no, sorry, I phrased it wrong. I want to hit Z from some element of B, right? I want to find some element of B that hits Z, right? What I do is I know that there's some element of A that hits Z. I know that there's some element of A that goes through B somewhere and then hits Z. So what I do is I pick that somewhere. I find this point. So I call this X and I call this Y. And I say, okay, if X hits Z, then it must have gone through B at some point. I just pick that point in B. That point goes from G and hits Z. Okay. This point will satisfy G of Y equals Z. That's kind of a diagram for the proof. Okay. Great.